Which year was that?
2009 to 2015.
All right, I think we can get started. So today we are so happy to have Dr. Howe from Fermilab to talk about physics beyond the weak scale and future collider facilities. Especially, he will be making a connection with the Chinese proposal, CPC, SPPC. Could be a circular electron-positron collider or Chinese electron-positron collider, as some people call it. So Dr. Howe received his PhD from Stanford University this past summer, right?
Yes.
Yes, under NSF grant. That's quite something, I think, as a graduate student. Yeah, it's like a fellowship thing, right?
Yeah.
Yep. Okay, so today is his first talk, and tomorrow Professor Zhang will be hosting Dr. Howe for the second talk. That will be more beyond the standard model. Okay. You have the floor.
Okay, great. Thanks very much for the introduction, and it's great to be here. I'm happy to chat with anyone. I'll be here for the next few days. So yeah, I'd love to hear more about what everyone's working on. Okay, so yeah, like we said, I'm going to be talking about future high-energy colliders and what we might expect from the future of this field. Okay, so I'm going to start with a little bit of a cartoon of where we are, how we got here, and kind of this is kind of a historical sketch of the current situation for high-energy colliders. Will give us lots of good examples for what we might expect to find in the future. Okay, so what are the things we know the most about? Well, those are the things that we're made of, right? So we're all made of protons, neutrons, and electrons, and we know an awful lot about those, okay? And of course, we also know about the photon, because the photon's very light, and you study the photon, you just flip a light switch, and you get a bunch of photons. So we know a lot about the stuff we're made of, and the things that we interact most directly with, especially when they're light enough that they're easily produced. Okay? Then something that lots of people in this room are interested in, of course, is neutrinos. And these are another layer of interactions away from us. So to get to neutrinos from the things we're made of, you need to go through the W and Z bosons, electroweak bosons. Of course, because neutrinos are light, and because we're made out of protons and neutrons, which can form substances that go through radioactive decays, this is still something that was discovered relatively early. Right? So even though these interactions are fairly rare, we can get a bunch of radioactive stuff and see what happens. And so we've discovered neutrinos. Though observing the properties of neutrinos has been a much more difficult and much longer route. And we're still learning very interesting things about neutrinos because we have to go through all these interactions to get to them. Okay, so this is one axis that's interesting to organize our understanding of what we can see with colliders on is, do things interact with the things we're made of, or something else, or how many layers of interaction do you have to go through to produce something? Okay, and then another interesting axis to consider to organize this idea of what we can study with colliders is the energy of the things we're producing. So everything we're made of is at the energy scale of around a GeV, or lower, like giga-electron volt. And we build colliders to accelerate protons or electrons to ultra-relativistic energies and study what happens in these collisions at higher energies and what we can produce. Okay. So we also had one other nice window is that we get a natural collider from cosmic rays, right, which we also have learned lots of interesting things from. And this revealed the existence of the light hadronic states. And in particular, a nice example of something you can find is that cosmic rays can produce pions, and we were able to discover the muon from the decays of pions. So discovering something that interacts with us leads you to a nice window through its decays to see things that are more distantly removed from the stuff we're made of. So pions opened up a window to be able to find the muon. Okay. Good. So the first things that we really needed colliders to study were to pin down the composite structure of protons and neutrons. So protons and neutrons made of up quarks, down quarks, and gluons. So understanding the QCD interactions and the structure of protons in detail required colliders. The discovery of the heavier quarks, so the copies of the up and down quarks that we're made of, it's like the charm quark and bottom quark, and discovery of the tau lepton. So these all happened at kind of early colliders operating at the scale of a few GeV, the tens of GeV. Okay, so that's kind of like the first era of particle physics. And the second era of particle physics, it really starts with exploring the physics of the weak scale and understanding the detailed SU2 electroweak structure of the standard model and pinning down the features of this. So at this point, there's a good picture of what we're looking for. And what you're looking for is to understand the interactions of the W and Z bosons and the rest of the electroweak structure. And so we've had a target that we've been going for the past 30 or 40 years with the high energy collider experiments. So, let's see. Okay, so the first target was to directly produce W and Z bosons, and this was the program of the LEP and SPS and a few other colliders of mapping out in detail the properties of the W and Z bosons at the electroweak scale. So, for example, LEP produced some electron-positron collisions producing on shell at the resonance, the Z boson, and studying all the details of its decays. Sorry.
No worries.
Yes, yeah, okay. Very counterintuitive.
Yeah.
Okay, and then the next big discovery is the top quark, right? So top quark interacts with the stuff we're made of. So it interacts with the strong force in particular. So there's a large cross-section to produce it once you reach the energy threshold required. But it's the heaviest standard model particle, so it required building a proton collider, a proton-antiproton collider, the Tevatron, that was operating at the TeV scale to produce this heavy particle. Okay, and then the last great victory of the high energy collider experimental agenda has been the discovery of the Higgs boson in the first run of the LHC. Right, so the Tevatron just missed it, and the Higgs was within the energy reach of the Tevatron, but it's, because it interacts rather feebly with the standard model particles, so to a good approximation, the way the Higgs was discovered at the LHC is you can think of the dominant production process for the Higgs as being, in some sense, the production of two top quarks, which then collide and produce a Higgs boson. So this is a very rare process, and it required the integrated luminosity of the LHC and the high energy of the LHC to discover this process. Okay. Okay, so this is where we are. We've discovered particles in a lot of different ways, and we have a few different directions we can go into the future of high energy physics, right? So the future on this plot is obviously this direction. We want to go higher energy, and we want to understand things that interact even more feebly with the stuff that we're made of. Okay, so let me talk about two concrete proposals for how to do that, and these are tied together in that both of these colliders could fit in the same kind of order 50 to 100 kilometer tunnel. So the civil engineering for these two projects is kind of a natural fit together. So these two projects are the circular electron-positron collider and the Superproton-Proton collider. So I'll give some details about these, but both of these have been studied in detail in an IHEP study. So there's a pre-CER preliminary planning document for this project that was produced at IHEP last year, and then also in the SNOMAS studies by the Department of Energy, in particular for the Superproton-Proton collider. There's been a lot of detailed studies of the physics potential for both these colliders. Okay, so what is the circular electron-positron collider going to do? Well, now that we have discovered the Higgs boson, we have an obvious target of producing as many of them as we can and seeing what happens. So what are the properties of the Higgs boson? what does it decay to, how does it give us access to new physics. So it's a obvious thing to do to build a machine that can produce as many of these as possible in a clean environment. So the process is just associated production of a Higgs and Z boson in the collision of an electron-positron pair. The center of mass energy that you need to do this is around 250 GeV, which is actually not much above the LEP energy. So this is a machine that we had decades ago. However, the integrated luminosity that you would like to have to study this process in detail is almost a factor of 1,000 more than was available at LEP. So getting the energy is, it's something that's been done. Getting the luminosity is a major development over LEP. Okay, and then there's also another option for this collider is to run it at lower energies and study in even greater detail the electroweak physics from the production of the Z boson, which is an interesting kind of fringe benefit of this kind of collider. Okay, so I should emphasize that kind of the big advantage of doing the electron-positron collider is that the LHC is going to produce a lot of Higgs bosons, especially in its high luminosity mode. But at the LHC, you produce a bunch of other stuff too. So because you're at a proton-proton collider, there's a high cross-section for lots of different processes involving colored products. And even when you produce a Higgs boson, it's a messy environment because you don't know all the kinematics of the process, and you have QCD radiation effects that complicate your event. So it's a great environment for discovering new physics, but for doing precision studies of physics, so for really nailing down the properties of a particle, it's kind of a messy environment. So this is kind of the main reason to think about an electron-positron machine. An electron-positron machine doesn't have as many competing processes and doesn't have as many backgrounds that make it difficult to study the Higgs production. Okay, so this is the kind of studying the Higgs either at a circular collider or possibly at a linear collider is the obvious next step for high energy physics. After that, it's a little bit more speculative what should come next, but what I'll talk about in this talk is the Superproton-Proton collider, which is, you can think of as just a scaled up version of the Large Hadron Collider. So take the Large Hadron Collider, make the ring much bigger, and increase the center of mass energy to somewhere around 100 TeV, so a factor of 5 to 10 more than the LHC energy. And kind of run it at the same, so similar set for comparable luminosity to LHC. So here the big win is non-luminosity, it's in the center of mass energy. Okay, and this will produce, this is an environment where you might discover new heavy particles is kind of the thing to look for here. Okay. So what does this look like in our plot? Okay, so the circular electron-positron collider, its energy reach is below the top quark threshold, so you're not going to do top physics here. Though there's possibly interest in a version of this that can explore top physics as well. But above the Higgs threshold, so you're producing the Higgs. And the big region that you open up when you have an electron-positron collider producing the Higgs is not a high energy region, but a region where you get to understand everything the Higgs interacts with. So by producing a lot of Higgses, we'll understand in detail all the things it interacts with. And that could be a lot of things. So one obvious thing is we know the Higgs should interact with the standard model particles in a certain way, and we would like to study that to as great of precision as we can, not only to verify the standard model, but other particles coupling to Higgs can cause deviations from the standard model predictions. So this is a very sensitive, indirect portal into if there's any other new physics beyond the standard model. There's also the potential for more direct probes of new physics with the Higgs sector. So if the Higgs has exotic decays, for example, flavor violating decays, or decays into a hidden sector that could be tied to the presence of dark matter, then you can directly study the production of new kinds of particles and new interactions that aren't in the standard model with Higgs factory. You can also study the properties of the electroweak phase transition by studying the Higgs self-interactions. And if you operate in the Z mode, you can study in detail electric precision observables. Okay, so there's a lot of potential here, and in particular in this direction of going beyond what we've probed in studying the Higgs, what the Higgs interacts with. The Proton-Proton collider is going the other direction, so it's going increasing the energy reach by as much as, so kind of the idea is to increase the energy reach by as much as is technically possible. You would like to go, if you could go to 1,000 TeV, you would go to 1,000 TeV, but I think 100 TeV is kind of the limits of the current, what is a feasible proposal for a next generation proton collider. Okay, and here we also get a lot of new things, new possibilities for physics, and they all kind of have analogs in the discoveries that were made earlier in the collider program. So, for example, you might discover quark compositeness. So this is the idea that there could be more fundamental components. The stuff we're made of might have a more fundamental description in terms of composite states. You might find new gauge groups. So just like we discovered the W and Z bosons, you might discover that there's additional gauge structure for how the standard model particles interact. You might discover additional matter interacting with the standard model gauge group. So you might, for instance, discover extra generations of matter. So the matter even heavier than the top quark. So a fourth generation of matter, for instance. Or if the part of the standard model is composite, you might expect that there to be colored or electroweak resonances that you could also discover. So analogs of like the rho mesons discovered at much lower energies in the excited QCD states.
Kyle.
Yes, yeah.
So you mentioned quark compositeness. Are you going to talk more later?
I will not talk anymore. Yeah. So
I have not heard that term for 10 years, maybe 20 years.
So there's a good reason.
Yeah.
What's
the story on that?
So lots of these things have quark compositeness, or just the presence of a strong sector, or the presence of any new states coupled with standard model, have pretty substantial constraints from a number of low energy observables. So rare decays, flavor violating processes, CP violation. What's interesting about going to a collider scale of 100 TeV is you're starting to get above the energies, or to energies where those low energy indirect observables are less constraining. So there's still constraints on physics at this scale from low energies, but things like flavor physics all start to be, all these rare processes become less constraining. So, in particular, quark compositeness has constraints from a number of observables that have been probed at other colliders, and depending on the flavor structure, there's lots of flavor constraints on this. But as you go to these higher energies, these things, it starts to become reasonable to talk about these things again. But yeah, so I will not focus on that. Yeah, good. Okay, right. So yes, or you might discover new electroweak states at this collider. So electroweak states are harder to discover at a proton collider because the dominant production cross sections are for colored states, and you have to compete with colored backgrounds. But it's another possibility for something you might find. Okay, so there are a lot of options for what we can find. There's a lot of exciting possibilities for what we might find going to higher energies. So what I'll primarily focus on is describing in a little bit more detail some of the possibilities for a proton collider. But let me just first zoom in on this idea of measuring the standard model Higgs couplings as circular collider, because this will be, not only is it one of the most compelling components of the circular collider, but it will also have a lot of effect on what you might think you are going to look for at a very high energy proton collider. And I should also mention that on this plot I have the LHC run 2, which we will hear some results from tomorrow very late at night. So that can have some interesting consequences, obviously, on what you might expect to look for at a future proton collider as well. Okay. Good. So this is a plot from the pre-CDR document about the Electron-Positron collider operating as a Higgs factory. And this is a plot of the precision with which you can measure the various couplings of the Higgs boson to standard model particles. In particular, just one example is the coupling to the Z boson. At the LHC in the high luminosity mode, you can measure most of these couplings to order 10 or 20%. So at the Electron-Positron collider, and most of these observables would be about a factor of 10 better. So in this example, you're going from 10% to about under 1% precision. So this lets you probe to a very high degree, is the Higgs really standard model-like, or does it couple to any other particles or have any extension of the Higgs sector from the pure single Higgs doublet standard model? Another interesting thing is that there are some couplings that the LHC, for various reasons, just can't access. So mostly that these couplings produce final states in Higgs decays that are very rare or very difficult to distinguish from backgrounds. So the two main examples are the coupling to the charm quark and the coupling to the muon. Right? So this is a very interesting thing to measure because right now what we know about the Higgs mostly has to do with its coupling to the electroweak states, to gauge bosons, and to the third generation of matter. So really, with regards to flavor, we don't know much about the Higgs yet. And this circular collider the circular electron-positron collider has the chance to reveal a lot of that. Okay, so what could all this mean? So if you measure deviations in the Higgs couplings, this could suggest a wide variety of new things that you could then go follow up and look for at, for instance, a high-energy proton collider. So one example is deviations in composite Higgs models. So the Higgs is a composite state, not a fundamental scalar. There's a strong correlation between these theories and deviations in Higgs couplings. If the Higgs is an extended sector, so there's other weak charge states that the Higgs mixes with, then these universally lead to coupling deviations. If there's any new matter that couples the Higgs and is charged in a standard model gauge group, then loop processes, so couplings through the Higgs producing virtual pairs of these particles and then decaying to standard model gauge bosons, also induce kind of universal coupling, universal deviations in the Higgs couplings. You can also, once you have an electron-positron collider, you can do a very detailed measurement of the branching of the Higgs to invisible states, so things that don't interact with our detector materials. And that tells you that if you observe a Higgs are invisible with, that might be a connection to dark matter. So it's possible that the dark matter of the universe interacts with us through only the Higgs boson, and you might be able to explore that. Or you might, even if it's not dark matter, there might be dark sectors that couple to the Higgs through this Higgs portal, and that might be the only way we have of exploring them. And then with regard to flavor, if you measure something unexpected in this, in these couplings to second generation matter, this might suggest looking for, this might suggest possible signals in flavor experiments, so in these low energy rare decay experiments. So this is another interesting direction that these measurements might take you. Okay, so yeah, kind of Higgs coupling deviations either measured in the 14 TeV high luminosity run of the LHC, or at a electron-positron collider at a factor of 10 better, are kind of the canary for new physics in the electroweak sector of the standard model. So anything here would be very exciting and would strongly suggest following up with a higher energy collider. Okay, so something. So something important for thinking about going to higher energies for a collider is, do we have a target energy? If I could build a 1000 TeV collider, would I want to do that instead of a 100 TeV collider, or is there a reason to think that physics should, if there is new physics, I should see it around 100 TeV? And the link between energy scales in the standard model and beyond the standard model, there's a few different things I can link, but naturalness, so there's a concept called naturalness, and dark matter are the two ideas that can link the weak scale to the scale where we might see new physics. Okay, So the idea of naturalness can be phrased kind of simply as, this is the plot I showed you where all these new states are appearing within the reach of the 100 TeV collider. And the question is, why didn't I show you this plot where there's all this new stuff that can happen, but it happens well above the reach of a 100 TeV collider? Okay, and in fact, we have lots of motivations reasons to strongly suspect that there are new particles that we can discover at some energy scale. So UV completions of gravity provide one strong motivation. Baryogenesis and the axion solution to the strong ZP problem also very strongly suggests new physics. The observations of inflation in cosmological observables, the patterns in flavor physics, and the possibility of gauge coupling unification. So there are a lot of motivations for why we might expect all these different kinds of extensions of the standard model. But none of these motivations that I listed require this to happen anywhere near the weak scale. So anywhere near the scale of 100 GeV that we've probed so far, or near the scale of hundreds of TeV where we might hope to probe with a future collider. Okay, so the question is there something that can tie these scales to the weak scale? Okay, and I will talk about one example, and I'll give a little bit more detail about how this works for the case of supersymmetry. But there are a few, so supersymmetry and composite Higgs models are the two kinds of models that provide a connection between these scales. And I'll talk about, I'll talk a little bit more detail about the supersymmetric models. And then the experimental thing that suggests looking around here is that particle dark matter, many implementations of it just won't work at high scales. So unlike all these other puzzles that you might be able to resolve at energy scale, particle dark matter generally likes to be resolved under 100 TeV. So this is another motivation. Okay, and supersymmetry and particle dark matter will motivate the detailed things that I'll talk about later. Okay, so we have this whole space of states of new things that we might be able to find at collider. Obviously, I'm not going to talk about all of it in one talk. So in the framework of supersymmetry motivated by naturalness, I'm going to talk about the potential for a 100 TeV-ish super proton-proton collider to discover new colored states that decay to new electroweak states. So this is a nice benchmark. It's similar to things that the LHC is already looking for. So we'll be able to scale up some search results. And kind of going through the details of understanding what is the reach of a new collider for these states gives a good example of how you can look at the reach for all these other types of new particles I won't have time to talk about. Okay. Good, so let's describe searches for supersymmetry at a super proton-proton collider. Okay, and so first I'll give just a brief review of supersymmetry and some of the motivations for it. Then I'll talk about kind of a simplified way of understanding what the collider signatures of supersymmetric models are. That's very useful for understanding experimental searches. And then I'll just describe in a little bit of detail some of the search and discovery strategies for supersymmetry and how we modeled those for doing a pilot study for a 100 TeV collider. Okay, so supersymmetry, the basic idea is that at some so the standard model, we have every reason to believe, is an effective field theory that describes physics up to some energy scale, which I'll call lambda VSM, which is a scale of new interactions or new particles that interact with the standard model particles. Okay, and the interesting thing that happens is if the Higgs boson couples to any of these particles, then there's a natural scale for the Higgs mass which sets the electroweak scale, which is related by a loop factor but is essentially proportional to this high energy scale. So because the Higgs boson is a scalar, its energy scale is naturally drawn to any other energy scales in the problem. So from an effective field theory perspective, you can just write down a mass operator sensitive to a new scale for the Higgs boson, or if you want to talk about it in loops, the Higgs, you can easily draw a diagram where the Higgs produces a particle and is where the Higgs couples to a pair of virtual particles, and that loop is cut off quadratically by whatever the scale of new physics is. Okay, so this gives a connection between this scale, lambda VSM, and the electroweak scale, which is just basically set by a loop factor. Okay. So this is interesting. Some of these scales we know must be much higher than the weak scale, though, for example. So one example is the scale associated with the UV completion of gravity must be much higher than the weak scale, at least a factor of 5 or 10 TeV. Right, so this creates some tension as we know, and there are probably other higher scales associated with gauge unification, neutrino mass, flavor. So it seems like there's very likely energy scales much higher than the Higgs, than the weak scale associated with particles interacting with the Higgs. Okay. So why is the Higgs boson, why is the weak scale not up at those other scales if it's tied to these scales in this way? There are a few ways to solve this problem. One of them is supersymmetry. And in supersymmetry, the basic idea is that you introduce new particles at a scale m SUSY, which is at or below this scale of particles coupling to new particles coupling to Higgs, where you introduce a set of particles that cancel the effects of other particles. Okay, so I will, for example, if this was a Higgs coupling to two top quarks, there's a scalar particle that has properties related to the property of the top that can propagate and couple to Higgs and cancel these loop corrections. And there's a symmetry between these particles that guarantees that this effect cancels these contributions. Okay, so now I can cut off these contributions, and I can get a there's still a contribution to the mass of Higgs, but it's proportional to not the mass of all states, so in particular, for instance, not the mass of the states completing gravity, but just related to the mass of these states that make my model supersymmetric. So if the mass of these superpartners was the exact same as the mass of the standard model particles, then I would have no corrections to the Higgs mass. And if this mass is heavier, then I get corrections, but they're proportional just to this SUSY mass squared, and they're protected from any contributions at much higher energy scales. So this is the basic idea behind supersymmetry. And this functions, there are other mechanisms for solving this problem, and they function in a similar way. So SUSY is also a good kind of toy model for how this might work in other models, like composite Higgs models. Okay, so the result of this is that we should expect to find the scale of these superpartners if supersymmetry is the solution to this problem. We should expect to find them around the weak scale. You get a little bit of leeway from having these loop factors, and maybe there's some accidental cancellations. But the idea of naturalness is that you shouldn't expect any cancellations that are very large, that give you a mass scale for the Higgs that's much smaller than this contribution that you get from loop level. So this is the principle of naturalness, is saying that I should expect to find things where this loop factor tells me they'll be. Okay. So that is the motivation for thinking that the scale of superpartners might be near the weak scale. Of course, that idea of naturalness could be wrong. An interesting thing is everything we've observed so far in particle physics obeys this idea of naturalness, that loop corrections, the natural scale for radiative corrections to particles doesn't differ very much from the scale that you find them at. So this has been a successful description of reality so far. So if you look for naturalness and don't find it, that is also an interesting result, because everything in the world that we've observed so far kind of fits this description. So you would hope to see these new states, but there's also something interesting to be learned if you don't see these. And so understanding what the limits are on these kinds of particles is an interesting thing to pursue. Okay. Good. So a little bit more detail about how this works for the standard model. So the standard model, I have my quarks, leptons, gauge bosons, and their interactions. When I make the standard model supersymmetric, I can introduce many new particles, but there's a minimal set of particles I need to introduce that are related just to the standard model particles. So the quarks, so the spin 1/2 particles, the quarks and leptons, get spin zero scalar particles that are related to them. So quarks get squark partners, leptons get lepton partners. And the gauge bosons, the spin 1 gauge bosons, get spin 1/2 partners. These are, so the electroweak the electroweak gauge bosons and the gluon that carries SU3 color get paired with spin 1/2 states, the neutralinos and charginos, which are don't have color charge but have weak charge, and the gluino, which has color charge. Okay. And the interactions of these states are related by the symmetry to the interactions of the quarks and gauge boson, of the standard model particles with each other. So for example, the interaction of two quarks, so a quark radiating off a gluon, for example, is related to the amplitude for the interaction where a quark radiates a gluino and becomes a squark. So these are all related to each other by the symmetry. So though I've introduced a lot of particles, I have a lot of structure of this model that tells me what types of things I should look for. And this is dictated by the symmetry. And this structure is necessary if you want to solve, if you want to have a solution for this naturalness problem. Okay, good. So we've introduced a lot of stuff. It'll turn out that the most important states, so you can study a lot of things about these models. You can study dark matter in these models. You can study their contributions to rare processes. What we're interested in talking about for this talk is just the reach of a proton collider for finding SUSY models. And so you can learn a lot about this by just focusing on a small subset of particles. And the most important particles for talking about a proton collider are going to be the ones that are produced most often. So those are going to be the squarks and gluino, because those are the particles that carry color charge. So they interact most directly with the protons that we're colliding. And the particles that these squarks and gluino decay to. And in many cases, we can approximate the behavior of the decays of the squarks and gluino by just worrying about how they decay to the lightest superpartner, which is often in one of these neutralinos and charginos. So we'll just focus on the case where I'm worried about how do squarks get produced and decay to neutralinos or charginos, and we'll focus on the neutralino in this case. Okay. Okay, and as we'll call these, this is the simplified model approach to looking at collider reach for supersymmetry. Okay. Okay, so let's start with the most simplified model that I could write down for trying to understand what I can do with a proton collider. We're going to use 100 TeV as our benchmark, so I have two protons colliding each other with 50 TeV each. The proton is made up of quarks, right? So in particular, there's some probability to have an up quark and an anti-up quark carrying a fraction of the energy in the proton. So you never get the full 100 TeV of energy in a proton-proton collision, but you get some fraction of it contained in the constituents of the quark. So, for example, you might get an up quark carrying maybe half the energy and an anti-up carrying a third of it. And then these two particles interact and produce some new physics state. So the reach for producing new states is kind of given, there's a kinematic limit for how much energy these particles can carry and still have a chance, like what is my chance of finding two particles that have a center of mass energy of greater than 20 TeV if I have two protons colliding at 100 TeV, right? So this is the 0th level question you can ask, and this turns out to be a reach of about 20 TeV. So at the luminosity of a few autobarns at a 100 TeV collider, I have a non-vanishing chance of producing some strongly coupled particle that has a pair of particles that have masses around 20 TeV. And above that, I don't have a chance. And this is, not surprisingly, a factor of 5 or 10, depending on the collider energy, more than the reach at the LHC 14. So this kind of just scales with the energy of your collider. Okay. So this is the 0th level answer about how you scale results from the LHC 14 or LHC 8 to higher energies. So what you would like to do is understand a little bit more what this collider can do and what we need to know about these processes for really understanding if an upgraded collider can look for these particles. So what you would like to do is look at a more realistic search strategy and see if it really scales in this way, that just it grows with the energy. And you would also like to understand what you can learn about your detector. So the real goal is to understand the detectors and machine that we need to build to look for these new states. So you'd like to know if there's any constraints on what type of detector you need to see these states. Okay. So let's talk about these questions a little bit and how we can answer them. Okay, so I'm going to focus in particular on two simplified models, and they both will have this general structure that there will be some new colored particle with a mass under 20 TeV, because that's where my production, I have a chance of producing it at a 100 TeV collider. And there's some other neutral new particle that it decays to, which could be a dark matter candidate. There's a strong motivation for that, but it doesn't have to be. Okay. And this setup, as I said, is often motivated by this idea of naturalness, as well as a number of general considerations motivate looking for this kind of setup. Okay. And then so this colored particle decay to this neutral particle in some standard model states. Okay, so the first simplified model, which I'll call the split supersymmetry model, just has that the only colored particle we care about producing is the gluino. And this gives us the gluino-neutralino simplified model, where the gluino, I know its couplings because I know that they're related to the couplings of the gluon through supersymmetry. And what I find is that I have the gluino and just this single bino that it decays to. And the decay is always through gluino decays to two quarks and the bino. The bino we'll assume is stable, and it doesn't interact with the, it doesn't carry charge, so it won't interact with the detector. So when you produce this particle in detector, it looks kind of like a neutrino. So you don't see it in the LHC detectors because it's a very weak interaction cross-section. The other model we'll look at is the natural supersymmetry model, where we'll focus on just the third generation squarks. So the third generation squarks are the ones most directly tied to this question of can the supersymmetry make the standard model natural? And this is because the third generation particles are the things that interact most strongly with the with the Higgs. So third generation particles interact strongly with the Higgs, so their super partners also need to interact strongly with the Higgs. Okay. So here our simplified model will just be that we produce a stop quark, so the super partner of the top quark, and it decays to a top and a light fermion, also the bino in this case. So this signature is just the stop going to a top. So because of the structure of this case, I know that in this case it'll most of the time decay to a top and this light super partner. So this is a good approximation to lots of these models where I have a more complicated spectrum. Okay, so these are my two simplified models. The signatures at collider level are kind of, we've chosen these two models to give us a representation of more generic things you might expect. So we want to understand the performance of a detector for kind of a general set of states. So these you can think of as two benchmarks that give us a good coverage of the final states that you might want to be able to look for at a collider. So the gluino case gives you jets of, so jets are, when I produce QCD charged objects, they radiate gluons and other quarks, so I get deposits of energy that are spread out in the detector and detected in the hadronic part of the detector. So this gives us a search that's dependent on my ability to measure jets and my ability to reconstruct the missing energy, which is just their invisible products in this decay. And I would like to see that momentum is not conserved when I measure all the particles, which means I missed some particle that was invisible and left the detector. So just the same as how the neutrino was originally discovered. Okay, and then also the stop neutralino model has a more interesting set of signatures. So here you get B jets. So the B quark is interesting because it decays somewhat displaced. So you can identify the presence of a B quark by looking for decays in the detector that happen displaced from the interaction vertex. So displaced from the point of collision of the two protons. You also have leptons in these cases, so the LHC can distinguish, detectors can distinguish leptons from other kinds of energy deposits. And again, you have missing energy. And because you have a heavy particle, so the top decays through a W and B down to lighter particles, you have the possibility of not only identifying that you've produced this new particle, but identifying that it's decayed through this top. So because you know the properties of how the top decays, you might be able to pin down that it's decaying through a top and use the properties of top decays to become more sensitive to this state. Okay, so this gives a pretty good coverage of kind of the more general signatures and final states you might want to be able to look for in this setup. Okay, so let me talk briefly about how we actually do these studies. So the idea is going to be to simulate these processes using a realistic detector simulation and find out what the reach is at 100 TeV collider. So fortunately, because of the LHC, there's a very well-developed simulation framework for understanding the production, decay, hadronization, and detector response for particles at a proton collider. So these main workhorses of this are MADGRAPH, which is for simulating the matrix elements of the hard event, and PIDIA, which does the showering and jet matching, so recreates the entire decay down to light standard model particles. And then DELFS, which is a fast simulation of the detector responses. So for this study, we used a mock-up of what you might expect for a future detector that was created for the SNOMAS process. SNOMAS was this process of studying some future experimental options. Okay, and then you can compute the next leading order cross sections with a variety of tools. Okay. Right, so in some sense, because we have such a well-developed framework, you just need to turn up the simulation to 11 and just change the numbers on the energy. Okay, so we have a nice simulation and well-validated simulation framework for doing this. So we can kind of believe the results we're getting from these tools. Okay. Another issue is how do you simulate the background? So at the LHC, what you like to do most is measure your backgrounds from control regions and extrapolate them to your signal searches. Here we can't do that because we don't have a 100 TeV collider to measure our background regions yet, but we can do Monte Carlo studies of the background and validate them against things measured at lower energies at the LHC. So to study the backgrounds for these searches, there's a common simulation of 100 TeV backgrounds that we've used. Okay, this I'll skip. Okay, so let me talk about the results for this first model, for the gluino-neutralino model, or split SUSY model. Okay, so in detail, so we're going to produce a pair of gluinos in this model, and then the decay chain, which is just dictated by their interactions and the particle content of this model, will be, the gluino will decay to a quark and off-shell through a squark into this light particle, the neutralino, and another quark. So your final state for a single gluino is just 2 quarks and this light neutral particle. And for so if we produce 2 gluinos, so all these processes we're studying involve pair production. So you don't produce a single gluino, but you produce 2 gluinos at once. So in these models, there's no amplitude to produce a single gluino, so you're always producing them in pairs. And so your final state is just 4 quarks, which will end up being jets, and 2 invisible particles, which will be this idea of missing energy, things I didn't measure in my detector. Okay. So what we've done is just basically scaled up a search that was used at the 8 TeV LHC to see how it performs looking for these states. Okay. Okay, so obviously it would be easy to look for these things if they were the only things I was producing at my collider, but there are lots of background processes that produce signatures that are similar to what you would like to look for to discover these particles. So kind of the canonical example in processes that involve missing energy or invisible particles is that the Z boson likes to decay to neutrinos, so it has a large branching fraction to decay to neutrinos, and those are invisible in our detector, so we can't tell neutrinos in our detector from any new particle that is invisible. So that's kind of an irreducible background, is that neutrinos look like any invisible particle. So it makes it hard to see if there's a new visible particle or just neutrinos in your event. Okay, so in particular, you can have events where I produce a Z boson that decays to neutrinos, and then I radiate some additional jets from my initial state. And this looks very much like the signal that I described. So this is what limits the efficiency of these searches, is that I have to overcome this background, so I need to look at cuts that reduce this background, and in regions where this background is dominated by my signal. So this is just a plot of the different distributions as a function of the missing energy. And one interesting result in this is that, so Z plus jets is one background. There's another background that is, I produce a pair of top quarks, and also they have decays that lead to neutrinos, and can be produced in association with jets. And this background actually becomes more important at 100 TeV collider, and this has to do with the set of cuts you use and the fact that at an 8 TeV collider, the mass of the top quark is still kind of a relevant scale. So top mass is 170 GeV, and that's when you look at the collisions energies that you're most sensitive to at the LHC, that's not such a large distance away from the LHC energy scale. But at 100 TeV collider, the top is to leading order massless, right? So so there's kind of it's a qualitative change between physics at 10 TeV. So physics at 8 TeV and physics at 100 TeV is that the top mass is no longer really a relevant scale in the production of particles. Okay. Okay, so the basic idea is just to look for the total amount of energy in the event and the amount of missing energy and figure out an optimal set of cuts for each particle, for each set of masses. So the axis I want to do this on is just, because I've taken this nice simplified model, I only have two parameters, right? So I have the gluino mass, which is setting how likely am I to produce this state and how much energy is there in the decay overall, and the neutralino mass. So what happens is if the neutralino is almost the same mass as the gluino, then there's not energy left over in the event to go into the jets. And so I see an event where very little happens in the event. So this makes it very difficult to see it. So there's this horizontal, or this diagonal line on the plot where the gluino and the neutralino are degenerate with each other, where it's very difficult to see this signature. And so what I see, so this is a plot of the discovery reach for the state at various colliders. And what I see is that my reach at this diagonal line dies off. But as I go, if I stay at a small fixed neutralino mass, then my rate scales up. So then I get a large reach for the gluino mass. So this is what's going on with this shape, this curve. Okay, and the overall conclusion, so you can validate this study we've done by comparing to experimental 14 TeV studies, and we find good agreement with the existing results. And from the LHC8 limit of 1.3 TeV, you improve by almost a factor of 10 by going to 100 TeV. So this is kind of a simple demonstration that 100 TeV collider, even though the physics is changing, for instance, the top background is changing, you still are getting this dramatic improvement in search reach that you would like to get. Okay, and in some sense, because this is such a simple final state, it's not really a surprise. So it's a nice proof of you go through all the details and it works like you expected, but it's not a big surprise because jets and missing energy are a fairly simple thing to measure. So there wasn't a lot changing between this search at 14 TeV or 8 TeV and 100 TeV. Okay. But yeah, a nice proof of principle that what we're doing is making some sense. Okay, so now let me talk about a little bit more complicated case, which is the stop neutralino model. Okay, so this signature, like I said, the stop decays to the top and this neutral new particle. And the things that make this search difficult are one, the top is decaying to a more complicated state. So it's not just a simple jets plus missing energy, but often the top decays to leptons, which is the leptons, it helps you to have the leptons. So leptons are less background-like than jets, and you can measure them better at the LHC, so they're a useful thing to look at, but it also complicates the search. And then, good. And the other thing you're fighting against is the stop, it turns out, has a much, much smaller production cross-section than the Galeno. So even though it has a more distinct final state, it's sensitive to backgrounds that have smaller rates as well. So you're fighting against these two things. Okay, and what I've plotted here is just at the 8 TeV LHC, they've done a number of dedicated searches for looking for this kind of decay. And they work in different final states, so you can have final states that have 1 lepton, 2 leptons, or all hadronic, and they all have kind of comparable reach. So we're going to focus on a single final state, where we're going to focus on the single lepton final state. Okay, so here, in the previous search, not a whole lot changed between 8 TeV and 100 TeV. There's a difference in the top background, but overall it's fairly comparable. Here, there's a much more important difference, which is again related to the fact that at 100 TeV, the top mass is a small scale compared to 8 TeV, where it's a fairly large scale. So if I have, at 8 TeV, I was sensitive to searches that had maybe at most a 700 GeV stop. And when I have a 700 GeV stop decay, then the energy of its decay products, so this top that it produces in the decay, is around the top mass. And so when the top decays, its decay products go in all directions. So it's not moving very fast. It doesn't have a high boost, so it's not very relativistic. So its decay products are somewhat fairly close to isotropic. Okay, at 100 TeV, I'm going to be sensitive to a scale that's about 10 times that for the stop mass. So I'll get decays where I am starting from a 7 TeV stop, and then I get tops that come out that are ultra-relativistic, that have carry an energy 20 or 30 times their mass, right? And in that case, I get decays that are collimated. So I find decays where my neutrino, lepton, and B quark that I get from the decay are all in a small cone, right? So I can. This is a very simple, right? The radius of the solid angle that I decay into just scales like the boost factor. So it's scales like 1 over the gamma boost factor for this relativistic particle. So I find that, well, had a very wide cone at 8 TeV, I can get very small cones that are challenging the limits of identifying objects at the LHC. So when I look for objects in the detectors at the LHC, usually I look for objects that are isolated from each other. And in fact, many of the searches veto events or get rid of events where different objects are close to each other because it becomes hard to disentangle them. And in particular, most of these searches you want to use the lepton and the B-jet. And there are lots of backgrounds for these particles that produce leptons and B-jets that are collimated with each other. So this is, in some sense, you're worried that this is going to hurt your, that if you just scale up an 8 TeV search, it's going to not be able to use a lot of events where these products are close to each other in the decay. Okay. So this is an interesting case where the physics actually changes between 8 TeV and 100 TeV. Okay, so there are many possibilities for how you would like to overcome this, and people have started to study a lot of these. You can try changing your parameters for how you look at isolation of these particles, or if you want to identify this B quark, then you need to worry about how it interacts with or how your detector measures this displaced vertex when there's another particle being produced nearby it. So these are good ideas that are fairly sensitive to the details of the detector, which unfortunately we don't have a very detailed model of what the LHC detector, or LHC-like detectors, so, or rather I should say, for these studies, we've basically scaled up the LHC detectors, and we don't have a good detailed model of what a 100 TeV detector will be. In particular, kind of the granularity and performance of the detector can make a big difference in how these different strategies affect this kind of search. But there are a few simple handles that you can use that are fairly generic. So the thing that will be useful, most useful in this, is instead of instead of doing some complicated thing to figure out this top, just look for this idea that there will be a muon that's overlapping with a jet. This is, you can call this a top tagging if you want, but it's kind of the simplest form of identifying a boosted top quark that you can imagine, which is just ask, is there a hard muon overlapping with a jet? And this turns out to work very well. Okay, so this is what we've adopted for this search, and I think is kind of a lower limit to how well you can do with this more complicated strategies. Okay, so this is just a cut flow table of how much each cut that you do on the vents reduces the background compared to the signal. The takeaway from this plot is that doing this, looking for a muon in a jet, this kind of minimal top tagging technique reduces the background by a factor of 10 compared to the signal. So it's a very useful thing to do. Okay, so what are our results from this? So at LHC8, you were able to find a 700 GeV stop. At LHC14, probably a 1.5 TeV. 100 TeV collider is going to extend the reach of the stop to around 7 TeV, which is a pretty interesting scale. So the MSSM has this problem that in the minimal version, it's hard to get the Higgs mass to be at 125 GeV, so the observed pole mass of the Higgs. Once you get into this region of multi-TeV stops, it starts to be much easier to get that. So this is an interesting range to be able to probe to. Okay, so kind of summarize results of the search. You're entering a new kinematic regime where you have boosted tops, but there are strategies that are simple and fairly robust for getting still very strong results that aren't significantly degraded from what you might expect from LHC8. And just taking a muon in a jet is one example. And the overall discovery reach is entering some interesting regime for the properties of the Higgs. Okay, so good. That brings me to the end. So let me conclude overall. So kind of having zoomed in on this area of these two simplified models, there's a lot of room for discovering new physics at 100 TeV proton collider, right? So you might have expected to discover anything up to a 20 TeV particle, and there could be all types of new things there. And I think these two simplified models give a good benchmark for the kinds of reaches you can expect. So for a colored particle with a large cross-section and a fairly simple topology, towards decay, you're getting to discovery reach that looks like around 10 TeV. And for states that have smaller cross-sections and are decaying through third-generation particles, where you have to pay branching fractions and have a slightly more complicated search strategy, you're decreased by a little bit, so maybe 5 to 10 TeV is kind of the range you can expect for these exclusions. But in both cases, this is a strong case for a future collider that can improve by a factor of 5 or 10 over our current limits or our future limits from the LHC14. Okay, and this can tell us a lot of things about the possibility of dark matter, the Higgs mass, and naturalness in the context of specific models like the MSSM. And it also suggests that we have a strong reach for looking for new things, even if it doesn't fit in this framework of the MSSM or some simple model. There's lots of possibilities for finding TeV scale physics. Okay, so on this plot of interactions and energy, I've talked in detail about this one example, and yes, it looks like we can do a good job of finding colored states decaying to new electroweak states. So I just want to emphasize in ending it that having these 13 TeV results and the potential results of a circular electron-positron collider could give us a lot of hints about what we're going to look for at a future proton collider. So, for example, if the 13 TeV LHC finds some new resonance, that will suggest, that opens up the possibility of a machine that can produce that new resonance and study its decays in detail. So depending on the mass scale, that might be a good candidate for this super proton collider, but it might also be a good candidate for a linear collider, right? So there are things that can happen at the 13 TeV LHC that will affect our viewpoint of where we should go in the future. And likewise, at the electron-positron collider, in particular, those measurements of the Higgs couplings are a very sensitive probe of if there are new states. So there are lots of new states that can exist, in particular, new gauge-coupled states, so states that we produce through the gauge interactions that don't interact with the Higgs, that could exist without producing effects at the electron-positron collider. So it's hard to use the electron-positron collider to rule out the possibility of finding something at a upgraded proton collider, at a 100 TeV proton collider. But if you do see something at electron-positron collider, in many cases, in almost every case, so there are a few counterexamples, but many cases where you get deviations in Higgs couplings involve new particles that you can produce at an upgraded collider that might be just within reach. So if you do see something at an electron-positron collider, then it's a very strong motivation to build one of these upgraded machines. Okay, I think with that, I would like to finish with a set of question marks describing our future. I think there's a lot of exciting questions to be asked. I think as you project more into the future, so in 2 days we'll know more about the start of the LHC run, and in 50 years we'll know about the results of the 100 TeV collider. But I think there will be interesting questions that will be asked and answered at all of these machines. Okay, and if you have any interesting questions now, I'd be happy to talk about them. Thank you.
LHC run 2 cannot find supersymmetry.
Mm-hmm.
So is the supersymmetry nature of?
Yeah, so what is your, it depends what your cutoff for naturalness is. I think a good way to think about that question is, what am I willing to admit in additional structure in the model beyond the MSSM? So the naive, simplest thing, if I just take a scan of the minimal parameter space in the MSSM with some UV completion, is that you'll be tuned to around 1% after the result of the LHC14, which means there's a 1% cancellation in the loop contributions to the Higgs mass versus the observed Higgs mass. So that's kind of calling in question this entire motivation from naturalness of expecting new physics by the weak scale. However, if I go beyond the minimal particle content of the MSSM and start looking at for example, natural spectra models where I have a good reason that I've explained why the third generation is lighter than all the other generations, I can reduce that tuning even at the LHC14 to a factor of 10% to 50%, which from the point of view of tuning, it fits this criteria of naturalness. But then, if you start to draw a plot of tuning versus complexity of the model, you've added a lot of structure to accomplish that. So I think what you will learn at LHC14 is that if you don't discover supersymmetry, there's more complicated structure at the TeV scale than just the minimal supersymmetric model. But I think it's still an interesting possibility to look for beyond the LHC14.
So when you do the prediction for a similar reason,
Mm-hmm.
can you extend your prediction to the time matter search? Like the IOSP node. Does your model say anything about that?
Good. So our model says, so in most supersymmetric models for the LSP, the dominant way that you produce it is through producing the colored particles that are heavier than it, which then decay to it. Just because the colored particles have such a larger cross-section, it's much easier to see those events. They have a larger cross-section and a much more dramatic signal than producing the LSP itself. But so our results can be interpreted in those models, but only if you assume something about the correlation between the LSP mass and the mass of the colored particles. So kind of the generic thing in most spectra is that the colored particles are within a factor of 10 in mass of the LSP. So getting a limit on a colored particle of around 10 TeV implies a limit of roughly TeV scale for the for the not-colored charged particles. People have also studied, you might like to do, especially outside the context of supersymmetry, where you don't necessarily have new colored particles associated with the dark matter. You might like to know just what your model-independent bound on new electroweak charged states is. And so people have done, so the signal for that is you just produce this electroweak state, and recoil off of a initial jet. So you just get a single jet and a missing energy near event. And there the limits are much weaker. So you still win by going to higher energies, but you don't get to really a TeV scale particle. But yeah, people have done this study for 100 TeV clutter. So there are a variety of additional studies for 100 TeV clutters that cover these are the possibilities.
So I guess then it's also possible to fold the dark matter search limits to the model, right? To your phase space constraint.
Like the direct detection searches?
Yeah.
Yeah, so a good framework for doing this is the PMSSM. So in the PMSSM, people have done scans over a fairly unconstrained parameter space of the MSSM. And yeah, you find that there are regions where the dominant constraint is dark matter, direct detection, and also spaces where your dominant constraints are collider constraints. So there's lots of complementarity between these searches. Yeah.
I guess the phase space is just too many dimensions.
Yes, it's a. I mean, what you find when you do these scans is that, so yeah, you might wonder from the simplified model framework, if I do this scan and find a much more complicated decay pattern than what I get in the simplified model. So say I have many particles in between my colored particle and my lightest neutral particle, you might wonder if I still get good limits. And I think one of the interesting things that's been, I think, fairly exhaustively shown by these scans is that you can get into parts of parameter space that the limits aren't quite as strong, but it's hard to do better than a factor of 2 compared to the limits you find for the simplified models. So there's still, in almost all regions of the supersymmetric parameter space, unless you have a spectrum that's basically everything at the same mass, there's a pretty tight constraint on the mass of the particles.
Yeah. If stellar neutrino really exist, heavy stellar neutrino. Is CPC or SPC helpful to find it? For example, generates this kind of neutrino beam for us to detect it.
Good. So, yeah, so that is very sensitive to the model that you use. So if you are doing a high-scale seesaw model, then you can always push the scale of these stellar neutrinos above the kinematic reach of these machines. I think one of the maybe more interesting, so there are models for neutrino mass with extra dimensions, so where you explain the hierarchy in neutrino masses by putting them into a large extra dimension, and there the scales can be more favorable for finding, discovering something about neutrino physics at these kind of clusters. There's also been studies just of low-scale seesaw models, so various kinds of low-scale seesaw models can be within reach, but it's a fairly model-dependent question in that case.
I guess with that SPPC, I think that the seesaw scale would become more natural. I mean, currently, Howe is the pioneer in this technology. I think he squeezed it really, really hardly to see whether there's one TeV.
Right.
That's
Yeah, it definitely gets easier. Yes. Yeah, this is another example where, so in that case it's just a issue of constructing a theory where it works. But it's another example where we know a lot. I mean, part of the reason maybe it's not so surprising that LHC 8 didn't find anything other than Higgs is that we know a lot about, there are a lot of constraints on what you could have found below 8 TeV from just issues of model building. There's a lot of stuff going on around a TeV scale with all the standard model particles. And then indirect constraints stretch up to 10 or hundreds of TeV for many kinds of rare processes. So this is, I think, another case where you start to have a lot more freedom when you go to higher energy from these indirect constraints. And so you might expect, there's more possibilities for what you could find.
So can the CPC or other SPPC can say anything with the Mariana neutrino demonstrate? Currently it's through neutrino double beta decay, but is there any?
Yeah, I don't think you can say anything unless you discover something related to the neutrino mass generation mechanism. So I think the case, if you discover lepton number violating processes, then this would give you a strong hint about the Majorana nature of neutrino mass. But it's another case where it could be within reach of LHC, but it could easily not be within reach of LHC if you have these lepton violating processes.
Other questions? Well, if not,